So, lecture 6.4, proportional, integral, or PI controller design. When studying steady-state error, which would have been chapter 4, we discovered that the more integrators in the open loop transfer function, the better the steady-state error. Remember, it also depended on what type of input you had, right? What type of command you had, and how many integrators were in your open loop transfer function. Those were the two things that mattered in terms of your steady-state error. So, PI control includes integrator compensation to a proportional controller without significantly affecting the transient response. Okay? Later, we will deal with how to design for transient response. So if you don't want to affect the transient response, you want to leave the root locus alone for the most part, but you want to include an integrator in there, so you're going to certainly change the root locus. So we're going to try to mitigate that change to try to affect the root locus minimally with our compensator, okay? Because we're just going to like lop it off and say, okay, with the integrator, we're going to try to, with the integral compensator, we're going to try to affect the transient response minimally, affect the root locus minimally. We don't really want to change it much because it'll change the transient response. Then when we do derivative control, we're going to use that compensator to affect the transient response. So that's our goal. So right now we're trying to not affect the root locus too much. We're going to try to not move it too much. We will move it a little bit, as we'll see, but it won't be significant. So here's the plan. Include an integrator. In other words, a pole at the origin in the controller, and a nearby zero to counter the pole's slowing effects on the transient response. So why does the integrator affect the transient response is a natural question to ask. If you add a pole at the origin, it completely changes the root locus. I mean, you can imagine even just the real axis rule starting at the far right when you're sketching the root locus, and you march leftward. As soon as you hit a pole or a zero, you have locus, then no locus, then locus, and no locus, alternating, right? If you put another polar zero on the real axis, which an integrator at the origin is on the real axis, you're going to change the entire real axis root locus, at least in the left half plane, and that's going to affect the entirety of the root locus. So you've got certainly a lot of changes that come in when you put an integrator in there. So we'll also include a nearby zero to counter the pole's effects. So we're going to put that pole at the origin, and then we're going to put a nearby zero to mitigate that change in the root locus. Okay? Okay. So let's use the angle criterion to understand why putting a nearby zero counteracts its effects on the root locus. Okay. So in this example, this is just an example, we have a root locus in green here, and we've got 3 poles that were in our original open loop transfer function, okay? So those were already there, and they define the root locus, which has, you know, this shape here. We've got oh wait, it's the no wait, that's it. So we're ignoring these two to start. So we have no locus, we have locus, no locus, locus. So one of the zeros is at infinity out to the left. One of them is at infinity out at this angle, 60 degrees, and then the other one's at negative 60 degrees. So we've got our root locus like that, and the angle criterion is met at every point on that root locus, right? So if we include a compensator pole at the origin, or an integrator, right, then that adds this, or subtracts this theta 1 angle from the angle criterion, and it messes up the whole thing. The root locus would look way different. But so instead of just leaving it as a pole, we also include a compensator 0 nearby, which has, if you'll recall, the opposite sign in the angle criterion. So pole and a 0 have the opposite sign. And if you look at the equation here, you see, so this was your an original pole, an original pole, an original pole. This is your compensator pole, and this is your compensator 0. So they arise in the angle criterion with two different signs, minus and plus. So if their magnitudes are the same, theta 1 and theta 2, or if they're similar, then their effect is effectively wiped out, right? They're just opposite signs and similar magnitudes, so they cancel each other out. So that's why we have to put that compensator 0 in there and put it in there close to the pole. Because if you put it in there close to that integrator, then those angles, theta 1 and theta 2, will have similar magnitudes, right? They'll be close to each other. So our theta 1 and theta 2 should have a similar value. If the 0 is close enough to the pole, then theta 1 will be approximately equal to theta 2, and the angle criterion will be essentially unaffected by the pole and the 0, okay, of the compensator. So that's like how we can understand why putting that 0 there is going to help us not affect the root locus too much. It will a little bit, and there's this whole sense of like close. What does close mean relative to how close the root locus is going to pass to these? So if you think about the root locus, if it went like this, then the two angles are going to be much different than each other in this region, right? For a test point in this region. This angle and this angle, one is 60 degrees, the other one is 120 degrees or something. Those are going to be significantly different, and the root locus will be significantly affected there. So if that is the case, what you have to do, that means that your 0 is not close enough to the pole. You got to move it closer to the pole. The closer you get to the pole, the more and more theta 1 will look like theta 2. Okay? But there's a balance there, as we'll see in the example. You're going to get a slower and slower steady state error compensation the closer you get that 0 to that pole. And usually we don't want it to be too slow. Okay? So this is usually a trade-off that happens, and we'll talk about that trade-off. But that's the general method. It's really actually pretty straightforward. The idea is put in an integrator because you want that steady state error to be good, right? So you put that in, and then you put in a nearby 0 to counteract its effects on the root locus, and you have to sort of play with that 0 location in terms of how close it really should be to that pole and what kind of performance you get out of that. And a lot of times you have to do simulation to really get a feel for how for where that 0 should really be. So we'll go through an example of that. But first, let's define a design procedure. So we can use this for what ends up being a pretty straightforward controller design. I mean, PI control, you do your proportional control design process. So that's step 1. Design a proportional controller to meet transient response requirements by choosing the gain and the dominant closed loop poles to be P1 and P2. So you design your proportional controller, but you've got some steady state error, okay? So then you want to have, say, for a step input or a step command, you want 0 steady state error as an example. So you decide to do an integral compensator. So include a cascade integral compensator, which includes an integrator and a real 0 near, and I put here, this is sort of rule of thumb. The real part of your poles here, your dominant poles, if you divide it by 10, you're going to be 10 times closer to the real, or to the imaginary axis with your 0. And that tends to be a pretty good place to start for deciding if this is going to be, or for playing with your performance. It's by far, or it's far from being the optimal position for every controller design. A lot of times you got to move this around quite a bit to get what you want from it. But it's a great place to start. It's a good. I mean, you have to choose something. So, choosing something like that is a reasonable place to start. So then tune the gain such that the closed loop poles are as desirable as possible. So when you put that integral compensator in there in step 2, you are going to affect the root locus. Even though you're trying to not affect it too much, you'll affect it a little bit because the pole and the 0 don't perfectly cancel. So the root locus will move a little bit, right? And you're going to want to retune your gain to try to get your optimal, or as optimal as possible, your controller performance for the transient response. And then step 4, simulate the time response to see if it meets the specs. That's the step we always conclude with, and then we tune accordingly. Maybe we need to go back and move that 0 around from the compensator. Maybe we need to go back and adjust the gain a little bit. Like those are our sort of tune parameters that we can change. Yeah, and if the steady state compensation is too slow, try moving the 0 leftward. So a lot of times there's a trade-off here, and we'll see this show up in the example, between the steady state compensation, steady state error compensation, and the initial sort of rise time and peak time. Usually there's a trade-off there that you can play with. And yeah, it depends on the situation which is more appropriate, the design requirements. Okay. So let's do an example. So if we had this plant transfer function given here, we want to design a unity feedback gain controller such that the system has 20% overshoot and 0 steady state error for step inputs. I said gain controller, but really what I mean is PI controller such that the system has 20% overshoot and 0 steady state error for step inputs. Okay. So we look at our plant and we see a couple things. First off, it is actually a second order system, right? With no zeros in it. So our second order approximation is actually perfectly accurate to start. When we put in the integral compensation, it will not be anymore because we're going to add a pole and a 0. So then we'll be up to 1, 0, and 3 poles. The second order approximation is certainly suspect at that point. And another thing to notice is that, okay, with the gain being 0, we start off at the closed loop poles for our root locus. So we start off at 2 stable locations in the left half plane, -2 and -5. Yeah?
So for the second order approximation, it was that you had, was it a 0 or a pole 3 times to the left of the 2?
Either, actually. So that's another sort of rule of thumb in terms of determining if your second order approximation is accurate or not.
And we're putting on the origin.
Yeah, which is to say, like, I mean, a lot is out the window. Although, as we'll see, if we put a 0 nearby, some of the effects of that pull at the origin are mitigated. However, you are still going to have a slower response to that steady state error response. So we'll see that show up in the simulation, where the steady state error will close much slower than the initial rise of the compensator. So yeah. So good. So this is a system that has, thinking in terms of steady state error, the plant has how many integrators? Seven integrators. We're talking one integrator. We're talking two integrators. How many are we talking here? What's an integrator again? Has to do with steady state error, am I right? Yeah. Maybe it's a factor of s that you can pull out of the denominator, like this. Yeah. So there are none, right? You can't pull out any factors of s from the denominator. So there are no integrators, right? We have s to the 0. So this is what we call a type 0 system, right? Back to chapter 4, the one lecture we had, 4.1, there was a table that had type 0 systems, type 1 systems, type 2 systems, and then different commands. So step, ramp, parabolic, and then you had different steady state error situations depending on which type of system you were and what type of command you were doing accordingly, right? So that was a nice, tidy, it was only a one lecture chapter, but that let us deal with steady state error pretty succinctly. So if you were to go back to that table and you were to see that a type 0 system has finite steady state error for a step command, and you know that we've got 0 steady state error as our requirement, we need to include an integrator in our controller. If you include an integrator, you'll be a type 1 system. And if you look up in that table, you'll see that a type 1 system with a step command gives you 0 steady state error, and you'll be good to go. So that is our approximate approach here, is that we're just going to include an integral compensator and get 0 steady state error. So let's start off by defining the transfer function. So this is just taking our transfer function and using ZPK to define sys1, which has a pair of poles at -2 and -5, no zeros, and a gain value of 10, right there. The desired closed loop pole location is along the ray corresponding to 20% overshoot, right? That was the one of the requirements that we had here, 20% overshoot. Since this is available with the data cursor in our Locus plot, there is no need to compute the damping ratio or the angle of the ray. Let us consider the root locus. So it looks like this. And this is the 20% overshoot ray, starting at the origin, going outward. The root locus is pretty simple. It just is along the real axis here, splits off, goes off to infinity, to zeros at infinity at 90 and -90 degrees. So this is the root locus. We can adjust the gain. This is the first step in the design process, is to adjust the gain in order to meet our transient response requirements. So we want our pole, one of our poles, to be right there on the 20% overshoot line. And since we haven't included a compensator yet, that should be right on the money, right? That should be perfect 20% overshoot, because this is analytically what we expect. So gain of 4.9 gets us there. So this occurs at a test point of -3.5, real part, and J 6.84. So that's the coordinates of this point, -3.5 and 6.84, imaginary. So what we're going to do is we're going to put in an integral compensator now. So let's apply the integral compensator, and we'll put the 0. So we're always going to put the pole at the origin, for an integral compensator. And we're going to put the 0. We said a good place to start would be 1/10 of the real part of the dominant pole pair, right? So the dominant pole pair has real part negative 3.5. So we're gonna say 10% of that is negative 0.35. So a good place to start with our 0 in our integral compensator is at negative 0.35 on the real axis. So we'll do that. So where S real is the real part here, it's negative 3.5. So this is, I'll put a little comment here, negative 3.5. The compensate, negative 3.5 divided by 10. And the compensator is just going to be the transfer function with the 0 in the numerator. So that's negative 0.35 in the numerator. In the denominator, there's a pole that's at the origin, right? So that 0 here, that numerical 0 value, it corresponds to the integrator, right? We're using ZPK, so it's saying what is the pole location? Pole location is at 0. That's what we're saying there. And then it has a gain, so the 0.35 goes to 0C, the integrator goes to this 0, and then there's an overall gain factor here of just 1. So there's our compensator. And we can now build, so we're going to build this composite system 2, okay? So this is all stuff, the compensator and so we're going to put our original plant, our compensator, and the gain that we designed first, all into one object called sys2. So this is the open loop transfer function with the controller and the compensator in there, okay? But we're going to want to retweak the gains with this. So we're going to define it as system2, and then we're going to do another root locus on it and tweak the overall gain again. Okay, so that's what we do. Again, we do another root locus. And remember, our goal with this integral compensation was to not affect the root locus too much, right? So it does look quite similar. I mean, obviously, you're going to have a little bit of locus right there, right? That's always going to be there with an integral compensator because you just literally put a pole and a 0 on the real axis. It's always going to have that part. But the rest of the root locus looks pretty much the same. We did pull it a little bit to the right, didn't we? But not too much. I mean, it's gonna change our performance a little bit. And in fact, in order to adjust the gain to get back on that 20% overshoot line, we had to go to a gain of about 0.94. Okay, so if that gain was 1, that would mean that it was exactly the same as the first time, right? Because it's just multiplying the original gain. So K1 was 4.9, and then this gain is 0.94, which means that it's going to be 6% less than 4.9. So it's 6% different than the original gain we chose. Pretty similar, though, right? Not too far off. Now we can compare these two closed loop controllers. So we'll do one closed loop transfer function where we'll just use the proportional gain, K1, and the original plant, and we'll do feedback on that. So that's our closed loop transfer function for just proportional control. And then we'll do system 2, which is, this includes our original gain and the compensator and the original plant, sys2 does, and then our tweak gain, K2, right? We tweaked it a little bit, K2. So this is the compensated closed loop transfer function. So what we're expecting here, it's really good. I love this idea. Never do a long calculation unless you already know the answer, right? We're expecting that, unless we've screwed something up, we're expecting that we're going to get zero steady state error out of the system 2 closed loop, but system 1 closed loop we won't. It'll be finite, the steady state error. We're expecting that system 2 is going to have this a similar transient response to system 1 in closed loop, right? So we're expecting these things, and let's do a simulation then. We just use the step command to do the simulation, and then we do step info on them, and let's take a look. And it says 20% overshoot. Good. So we're good on that. Let's take a plot, and let's see. Let's look a little closer. So with P control alone, we get the blue line. And that blue line, notice, has a significant steady state error, right? It should be 1. It should be going to 1, but it's clearly not going to 1, right? It's going to something else. So this is our steady state error. And that's why we needed to do this integral compensation and do a PI controller, which is going to fix that steady state error. And we get this steady state error mitigation that happens. Notice that it performs pretty much the same in terms of its initial rise, right? The initial transient looks pretty similar to the proportional controller, which is what we expected, right? Because we didn't change the root locus too much on purpose. But we do get this nice steady state error compensation. Now is the point at which you have to sort of explore your design and decide, okay, maybe that's just where you want to be. Maybe you want that initial response that's quick, and then you want to have that steady state error that like slowly closes the gap. You want that error compensation. But maybe you want that to all happen more quickly. So maybe you want this to settle down to its final value quicker. Now, what you're usually going to have to trade off here, and you will in this case too, is that initial quickness with the steady state error quickness, okay? So one option, and I'll exaggerate it a little bit, is to move the 0 leftward in your integral compensator. So remember, we put that 0 pretty close to the pole. Now, you could go closer and closer and closer, but what you would see happening if you move that 0 to the right is that your initial rise would look closer and closer to the P rise, but then your steady state error compensation would be slower and slower and slower. So it would ooze up just slowly. Slowly. And it would take a long time. So that's usually not what you want. Oftentimes what you're going to want is to get to that steady state error being small quicker. So if you move that 0 leftward, usually that's going to happen, okay? Move that 0 leftward, and what you're going to see is that you're going to pay a price. And I'll try to exaggerate it a little bit. You're going to pay a price in the rise, but you'll probably get to your steady state value faster. So you're going to have to trade off between your steady state error compensation transient and your initial rise transient. And it depends on the design situation. It depends on what you need out of the system, what the performance is. It wasn't really specified in our design problem here, which is more important to us. So we didn't worry about. So we don't really have a way to answer this question. But we just know that there's a trade-off here, and if you're designing the controller, you have to figure out which is better for your design. Does that make sense? Yeah.
So like, I don't really have good examples for this, but if you ever drive like a golf cart,
Mm-hmm.
when you step on the gas, it's really slow to react. Could that be like from this? Like they focused a lot on making sure that the steady state was where it's supposed to be and less on like the reaction time? Or is that more like motor design?
I mean, what you're seeing there, I mean, specifically in that specific situation, is just the electric motor response to the throttle. So it doesn't have probably feedback on that, because so you can imagine, and I've thought about this before, like why don't we control cars by just having like a lever where it's just like the speed that you want to be going.
Like a lawnmower?
Or a boat.
Is that how? I mean, like, but that's like, isn't the boat too like a throttle thing? Yeah, but like, I mean, like set it to 30. I mean, like, think about just like cruise control being the only way you'd set the speed. Like, instead of having like gas and brake, just have this thing that says speed, and then you can just drop it down to 0 and you want to stop, and you can increase it to, 50, 60, 70, 80, whatever you want to get to.
Trains,
What?
how trains work, right?
I mean, I would believe it. Yeah. I mean, so that's and that's how cruise control works when it's engaged, although it doesn't usually go down to low speeds. But if you think about something with feedback in it, I would say if you're going to use like a vehicle example, I think that with cruise control, what you would notice with something like this is, if your cruise control reacts to, say you start going up a hill, say you're going along and you're set on 60 and you're going 60 and you hit a hill, and if when you hit that hill it doesn't respond right away and you slow down, you're like 55, and then like it slowly responds, and then it just like eases right to 60 then, like when it compensates. That would be more this situation. They went with this design where it's like, oh, okay, it's going to take us a minute to respond. But if they were to go the other direction with it and say, we want that initial quick response, so right when you hit that hill and you started to drop speed, you'd rev up. Okay, you'd rev up quickly and you'd get close to your set value. You'd get up to like 58, like really quickly. But then it would take a little while for it to actually get to 60. Like it would then it would have a little slower response to get that last steady state error out.
Okay. So you might like go to like 62 and then kind of 58 and kind of like bobble instead of being like slow but exact.
Yeah, you might have a little more of a quick response, and then like you can see here, like a quick response, and then it's like it goes overshoots and it comes back, and then it sort of like oozes back up slowly. In this one, it would respond more slowly, but it wouldn't have that long time to get to exactly 60. So it's kind of a trade-off in your performance given a different situation. So, yeah. Okay, I gotta shut this down because I gotta give you guys these things.